evaluating our predictive models, in particular how to evaluate our classifiers. So in a classification problem, our general task is to assign a decision class label to a set of unclassified cases based on a set of variables, given a set of pre-classified examples. So discover the classification knowledge representation to be used either as a classifier to classify new cases, a predictive or predictive or to describe classification situations in data as a descriptive perspective. So since our training examples are all pre-labeled, this is an example of supervised learning. So there are a multitude of classifiers we can use. Several of them we've talked about or we will talk about in this class. A couple of weeks ago we talked about decision trees, and last week we talked about support vector machines. Next week we'll talk about naive Bayes models. But the routine remains the same for each kind of model. We create a classifier based on our training examples, then we evaluate on a separate set of test data, and then we use this on new examples. It's called the train and test paradigm. So when it comes to evaluating our models, we can look at measures of accuracy, which refers to how long it takes, which tells us the likelihood of accurately predicting the correct class. The speed of the algorithm refers to how long it takes the algorithm to run, or for something like deep learning, algorithms can take days to run compared to many of the simple logistic models we have used run in less than a second. So depending on your goal, speed can be very important. Another option is how robust your model is. Does it keep its accuracy when given noisy data, or if you apply it to a data set on a different domain, how does that affect it? So the model I developed for the healthcare project, is it robust enough to go to a different industry like marketing? So other criteria pertain to scalability. Can your model handle large amounts of data? This may come into play if you use Excel versus R. In Excel, you're limited to the amount of data and kinds of algorithms you use, whereas in R, you can use significantly larger data sets and a wider variability of algorithms. Interpretability is very important. Based on your examples of logistic regression and support vector machines on the Lending Club data, you can see how interpretability affects our model. In the logistic regression, our coefficients are easy to interpret. However, in support vector machines, the coefficients of our support vectors are not necessarily easy to interpret. Simplicity is also important for actual implementation. It's easier to understand and use an algorithm that may be used or implemented by a manager than a complicated algorithm. And finally, the domain of the problem can be evaluated. In healthcare, someone's life could depend on the accuracy of your model, but in advertising, then the accuracy may not have as high an impact. So we can evaluate our models with different metrics. A simple accuracy metric could be to divide the number of correctly classified examples by the total number of examples. This percentage could then be used to compare several models. We could also look at misclassification error, or how often our algorithm is wrong. So we talked a little bit about this last semester towards the end. Start with an example of a confusion matrix for a binary classifier. So it can be easily extended to more classes and just make the confusion matrix bigger. So what can we learn from this matrix? Well, there are two predicted classes, right? Yes or no? If we were predicting the presence of a disease, for example, yes would mean they have the disease, and no would mean they don't have the disease. The classifier made a total of 165 predictions, so there was 165 patients were being tested for the presence of that disease. Out of those 165 predictions, or cases, the classifier predicted yes 110 times and no 55 times. In reality, 105 patients in the sample have the disease, and 60 patients do not. Based on that chart, we have four important values. The true positives, where we predict yes, and it actually is yes. The true negatives, where we predict no, and it is no. False positives, where we predict yes, but it is no. And false negatives, where we predict no, and it is yes. And that's where the type 1 and type 2 error come in. From those, we can calculate a multitude of metrics about the quality of the model. The first one is the accuracy, which is the true positives and the true negatives divided by the total. The true positive rate is also called recall, and is the true positives divided by the actual yeses. Here, the true negative rate is also known as specificity, found by dividing the true negatives by the actual negatives. Those that I mentioned are the ones we use when we start comparing different algorithms. There's other ones depending on where your data is coming from. Cohen's kappa is important for something called inter-rater reliability. So if you end up using like human subjects to look at data and tag it, if two different people were to tag that or label that set of text, let's say, and they both found the same thing, then your Cohen's kappa would be higher. But if they didn't find the same thing, then it would lower your Cohen's kappa. So it's trying to say that if several people were to rate it, how likely is your inter-rater, or it's a measure of reliability. So it's very important in text mining and natural language processing. It ensures that your results were not found by random chance. The second one, which I've used a lot, is called the ROC curve. It stands for receiver operator curve. It's very important to most classifiers. So depending on how you split the data will change your computed accuracy. But with an ROC curve is less sensitive to how you split your data. So you then find something called the area under the curve, or AUC, which is a better indication of predictive model accuracy. So the way we talked about with the confusion matrix, when we do set up our test and train set, depending on how you split that data will affect that accuracy value. But it will not affect as much your area under the curve for your ROC curve. There are a couple of ways we can empirically test for accuracy. With the use of the first way, which we have, is to randomly separate the data into a training and a test set. We typically do this with creating a training set of about 2/3 and a holdout set for testing our model to be about 1/3. A method that is very common. It's called cake. Here we separate the data typically into 10 equal subsamples. You then use 9 sets for training the model and 1 set for testing the model. Then you swap out 1 of the 9 for the test set and rerun the training and testing cycle until you repeat it 10 times so that all data has been both used as a training and a test example. You then summarize with the mean value across those 10 repetitions.
So the evaluation is the mean of all the 10?
Yeah, you'll typically use that more when you have, it's always more accurate, but you'll want to use it when you have a smaller sample size. When you have a whole bunch of data, then it's usually not a problem, and you can just use the training and holdout set. But to help get a better measure of your accuracy, it's better to do k-fold cross-validation on smaller data sets.
Okay.
So, like I was just saying, this method is typically easier on larger data sets, so doing a single random holdout should be sufficient. But as the data gets smaller, it is better to use a repeated holdout like the k-fold cross-validation. This is important because in small data sets, you may run the model and have zero or very few positive cases. So basically, with the cross-validation, we are trying to average out our error rate with each iteration. So kind of what I just said, though. So I put in a visualization here about what we're doing. So if we have five-fold cross-validation, we'd separate the data into 5 blocks, and then we'd put the first one as our test set and use the other 4 for training. Then we'd go to the second block and use it as test, and we'd use the other 4 for training, and we'd go to the third and the fourth until finally we're use the 5th one for test and the other 4 for training. And then we average all those values together to get our composite level of accuracy.
How do you know how many sets you want to use?
Let's see, should I say that on the next slide. So there has been extensive research on using 10-fold cross-validation, and that research states that 10 gives us our best estimate of accuracy. I guess it's what empirical testing of how many fold cross-validation is the best.
So to have 10 is the best?
But yeah, that's based on research of other people, yeah.
Well, how many observations do you got to have in that test?
I don't know. I'd have to look more into that one. It depends on which model you're actually using, because generally they'll have minimum sample sizes. For basic simple regressions, they'll have how many samples you need per variable that you have. But then other ones with partially squared regression, you want sample size of around 200. And then below that, it's hard to get a good model, and above that, you start getting models that are always statistically significant, so you have to look at other ways to verify it's doing what you want.
Oh, okay.
So it's dependent on the model type.
They decide this through research, or is it?
Yeah. Typically you're gonna see that more in statistics research, where that's their focus, is trying to promote one model or algorithm as being better than another.
Okay.
So, and then they'll go and do all this research and testing the models in different ways with different kinds of data, and say, well, previously we thought this kind of regression was better, but now we find that this new version is better. And it's a pretty heated debate if you ever read statistics research. So.
Okay.
So the last thing about comparing data mining algorithms is really the focus of this class. In general, you want to know which classifier works best for the domain you are working in. If you're going to implement only one algorithm, then you probably want to select the one that is most accurate. We can do this through cross-validation or calculating metrics from our confusion matrix. Also, if you compute the ROC curve and compare the AUCs for several models, that generally gives a pretty good indication of the quality. But just because, if you look at research papers that are doing this, they'll generally run, 4 different models. So they'll run the neural network, a logistic regression, a support vector machine, naive Bayes model, and then they'll show that the accuracy was best for support vector machine, specificity was best, and then you go to another paper and they are on a different set of data, and then the neural network will perform the best. So it just depends. But that's how a lot of research papers are designed, is they just compare different model types.
Okay.
And then in industry, generally, I guess it depends on the industry. I know in marketing, like at NBC, their accuracy doesn't have to be very good, and very tiny improvements in that accuracy makes everybody happy. But where I come from in healthcare, it needs to be very accurate and very close to being perfectly accurate, or it generally doesn't have good consequences. But I got for this week for something to think about. You have any questions or thoughts, or?
Not that I can think of.
Okay.